hear me? Yeah, good afternoon. And this is the title of my talk, the order effect and time varying category. Our story is quite simple, so I think I can just finish it quickly. Okay. The story actually starts from Navarro's study, so I have to introduce his study first, and then I will just say something about ours. So recently, Navarro and his colleagues shows that people can learn categories, even though the category structure is varying with time in some way. That's not a usual way to design the experiment, especially in the category length paradigm. However, they found that people actually can learn this type of categories, and they also show that the traditional, or we can just say the original prototype model and the example-based model like GCM cannot predict the data. And they also proposed a simple rule-based model, which is used as a heuristic to accommodate their data. And I was very interested in this in their work, so we just decided to expand their work by using different types of time-varying categories. And also, we also have another aim, that is to try to seek for a general account for how people actually learn this type of category. First, I'm going to talk about what is the time-varying category, and also I would like to put my emphasis on the order effect, which is I think is quite relevant to this type of task. However, the Navarro study did not mention that too much. And also, I'm going to show you three experiments with different types of category structure, and I'm going to compare three different types of models to be a map. Okay. Then let's just quickly refresh your memory about how people run the artificial category learning. Normally, the category structure is unchanged throughout the whole experiment. For example, if we have one-dimensional category structure, and then the experimenter define two categories. Let's say the category A and category B, and the two category boundaries here. And then on the outset of the experiment, the computer will just randomly pick one of the stimuli from the stimulus population. For example, let's say this is items from category A, and then the subject have to make their response, and then they will receive the corrective feedback, and then move on to the next one. So this time, maybe you just sample another one, which is from the category B. And just keep doing this way on and on until the end of the experiment. So you can notice that the category bound never changes throughout the whole experiment. Okay. However, Navarro and his colleagues run a very interesting change to this type of category learning task. They use this type of category structure. The x-axis represents the trial number, and the y-axis actually represents the stimulus value. As you can see, the stimulus value increases, the trial number increase. So which means the later the trial, larger or the bigger the stimulus. Okay, and the category boundary actually depends on the trial number. So that is, let's say, for example, this one. All right. For trial, maybe number 45 or number 47, and the boundary would be just number 7, just 47. And if we happen to have the item here on the same trial, look at here, and according to this rule, it should be classified as the high category. Let's say it's category 1, and the number 1 is the category 2. And however, when you just move on to some other trials, this one, the boundary just move up, and then if you have item on this trial happen to be here, then you just say, okay, it's smaller than the category boundary, then it should be category 2. However, this is not an easy task to do because the subjects didn't know when the boundary should be So what should be how large it is. So this is not easy task to run. And they find that actually they can learn these categories, although but it's better than chance level. And also the categorization accuracy for category 1 is larger than category 2. And in this particular case, it is reasonable because as long as you have the idea, for example, those items are keep going up, okay, sorry, keep going up. And if you happen to observe a very large stimulus, then you will be very confident to say, yeah, it must be category 1. However, if you have not that big, but probably it's bigger than the current one, then you might say, well, I'm not quite sure. Maybe it is category 1, maybe it is category 2. So it's not easy to make a judgment here. All right, and they also fit the original prototype modeling sample model to their data, and they found that it's work because these two types of models actually are insensitive to the trial order. And also they actually make some change to these two types of model to make them sensitive to the trial order, and then these two types of models can fit the data. Okay. However, they propose another one that is a very simple rule-based model. They say just use kind of a heuristic, and they say that this kind of heuristic rule model can provide a good account. But they didn't name the model, so I just called their models heuristic rule model. Right. So after I read their paper, I thought, wow, that's interesting. However, it also reminds me of the order effect. However, if you look at their paper, you will find, yeah, the key point is whether the model is sensitive to the order, right? If it is the key point, then there must be some kind of the order effect should be observed in this type of experiment. And in their original paper, I didn't find this kind of discussion. So I'm interested in, maybe we can just rerun the experiment and try to see whether there's some kind of order effect. And here the order effect I would take is the one actually reported by Stewart, Brown, and Chet in 2002. Suppose we just know that category 1 takes a smaller value. Okay, so that's here. And category 2 takes the larger value that's there. And now, if you just, I just used the mouse. If you get the stimulus here on trial number -1, and then you also know this is from category 1, and now you got this one, you will say, well, yeah, it must be 1 because I know the smaller should be category 1, and the previous is category 1, and this one is even smaller than the previous one. Okay, so this kind of a heuristic strategy. And also you can just find, for example, if you got an item on trial n-1 here, and you know that it is a category 2 example, and then you got another one from there, and you say, okay, now this time it must be category 2 because it is even larger than a large one. However, if you found the items having here, comparing to the n-1 here, it is not smaller, it's larger. So I don't know whether it is category 1, but well, I can just make some kind of judgment, like I just use the similarity between it and the previous one to make the classification for this one stimulus. So this is what they do, and they also pack the whole idea using the similarity and dissimilarity GCM model. Okay, so this is the motive of this study. First, I would like to extend the order effect, especially I would like to know whether in this kind of experiments, our subjects actually perform like what Stewart, Brown, and Chet expect. And also, I would like to try to extend the methodology study. In addition to using the ascending trend, I also use the descending trend and the quadratic trend, which would be C, like here. Okay, the first experiment use this capital structure, which is just this N, step one I just introduced you. And the second one, we just maintain the relationship between category 1 and 2, like it's the same as the experiment 1. However, the moving trend now is going down, so subjects will see the stimulus length is gradually becoming smaller. However, the tricky one is the experiment 3. In this one, we just use a quadratic category structure. And I also split the whole learning phase to 2 parts. In the first part, in the first section, category 1 is above category 2. Then in the second session, this pattern just flipped. So the category 2 is above the category 1. So let's see how I'm going to test the subjects. I just make it quickly. So just skip this. Well, certainly let's just say we have finished collecting the data, and then I'm just going to fit the model. Before I introduce you the data, I would like to just introduce you quickly the 3 models I use. The first one is the Navarro-Scale model. So that is just based on the current item and the current boundary to predict or to estimate the boundary for the next trial. So they just use the same way to go continuously and estimate the boundary of the next trial. And and based on the difference between the stimulus of the current item and the boundary, they will just use this sigmoid function to transform to the probability of category A or category B. Right. All right. Modified GCM is actually just the GCM, except I just made the influence of example decay along the trial numbers. Okay. And SDGCM is actually the model proposed by Stewart and Brown, which is the GCM, which is based it's based on GCM, but you just say that in addition to the similarity, but this similarity is also used for the people to make the correlation, and also this model is sensitive to trial order. Okay, so let's see the. Oh, sorry. Okay. When I'm going to show you the data, but before showing you the data, I'm going to just make a quick clarification. Yeah, we've collect the data and then we feed this model to the data. But when we feed the data, we just would like to check whether the model can predict the order effect. So the order effect can be separated to 4 conditions according to the preceding item, whether it is from category 1 or category 2, and the changing direction, whether you are larger than the previous one or you are smaller than the previous one. Okay. Now, this is the learning performance. And for in the experiment 1, this category structure is the ascending structure. And we just look at the solid line because those solid lines represent for the subject's behavior data. And you can see, initially we think that this task will be very difficult to learn. And so we won't expect that people can learn, how good people can learn. However, we found that people actually learn very well from category 1 compared to category 2. Of course, you can say, well, no, see the learning curve is coming down, it's not going up, right? Of course, you can say that, but comparing to this one, this is always at about chest level. Okay, and this is not surprising because I just reviewed the Navarro's studies result. They also find that category 1 is learned better than category 2. However, in the experiment 2, the learning performance is better for category 2 than category 1 because now the category structure is going down, right? So when you find a very small item, then you become very confident to say that it must be from category 2. Okay. Sorry, I don't know how to go back. Okay. Yeah. Right. And here comes the tricky part, is the experiment 3, the quadratic category structure one. And as you can see, category 2 actually learned better than category 1. If you just ignore the certain drop here. So the reason for this drop is because the leap at around about trial number 50, yeah. So the subjects just certainly got some shock. But if you focus look on the first section, because the trend is going down, it's descending, so you can expect that people will learn better in category 2. However, when you look at the second section, that is the category structure is just keep moving up. In that time, the high category should learn better, but we believe the categories, so the category 2 now is also learn better. Okay, and here comes the order effect. The order effect is, we just focus, we can just see that when the preceding category is actually from category 1, let's say here, and now, if I were the stimuli, okay, my value is larger than the previous one, which means I'm going up. Then people tend to predict this item as category 1, okay, in the experiment 1, because the category structure is keep going up. And also, they know that when the previous item from category 2, and then the current item is actually smaller than the previous one. That is, this one is called D2 here. And people tend to predict it as category 2. That's the observed data. And what happened for those two other conditions in between? For example, here, if the previous item is from category 1, but now my value is smaller than it. And I'm not quite sure whether it must be the category 1s. Then I decrease the probability probability of category 1 on it. Okay. And something like that, and we can find for the other condition in the category 2. And the model prediction, as you can see, the modified GCM sort of capture this pattern in these 4 conditions. And the SDGCM also, and heuristic rule with the model actually perform, it's okay, but it is not that good for this condition, but it's okay. And in the experiment 2, we can find the same pattern, because now the category 2 is still smaller than the category 1. Okay, I'm not quite sure, but I run out of time, right? 2 minutes, all right, thank you. So I just jump to this slide. Well, the pretty part is the order effect is very straight, because you can see in the first session we got the same pattern. In the second session, we find that because now category 2 is smaller than category 1, so when category 2 is larger than category 1 in the second session. So when you find the previous item is category 1, and then the current item is smaller than the previous one, and you are very likely to predict it as a category 1. So that's for the second session. Okay. As you can see, the modified VGCM and the SDGCM can capture this pattern. However, the heuristic rule-based model actually cannot predict this pattern. So, in summary, this is because the relationship between the categories is fixed. Actually, is fixed in the HR model, but our category structure actually break the category relationship. So that's why it is not good for them to adapt to the fluid structure. Okay, so here comes the summary. We have the 2 categories are not learned equally well, and also we found some response bias, which might be induced by the category structure. And also we find some clear order effect. Based on this effect, we will suggest that in addition to the long-term representation, short-term representation might be adopted for learning the categories. And also the example-based model is, in this case, is more flexible than the universal model. So that's it. Thank you.
Thanks, Lee Xieng. That was great. So in the modified GCM model, you allowed I guess the strength of each of the stored exemplars to decrease with time, to decay with time. Have you looked at how many exemplars you actually need in order to account for your data? Do you only need the previous 3?
Yeah.
So the previous 3 are what are you using? Okay, great.
Yeah, thank you.
This is really a naive question. I'm just wondering, do you have a real-life example for that we actually change the categorical membership as time goes on? The other thing is about the order effect. Is it always, sort of like a third there? It's always just based on the trial immediately preceding the current one, as opposed to say there's some pattern across. I don't know what's the boundary of the trial.
The flip, the category structure in nature, I'm not quite sure whether we find it or not. But we do have a lot of examples for the features to vary with time in the category, in the nature category. For example, if I ask you the question, which kind of plant has its leaves green in summer and gradually turn to red in autumn, then you probably say, well, that's an apple. Yeah, if you just apply it to, for example, if in summer you will say, okay, maple compared to another tree. Yeah, but in terms of the color of the leaf, then you say, well, the boundary is like that, and it's hard to tell each other. But in autumn, then just move on. So I'm not quite sure whether this is an answer to your question, but I think that the flip structure, sorry, I really don't know whether there will be a nature, but the time vary category are not equal, at least one. And the second question is, for the second question, well, in this study, we do not exclude any possibility that we rely on any long-term long-term representation or some kind of memory to help us to make the classification. But in this particular learning situation, since people never know what's going on next, right? So the only way for them the only reliable way for them to do some prediction is rely on the preceding one, just like one or the preceding 3 or 2 items. So if you say, could this experiments suggest that we don't need a long-term memory? I say no, of course not. But this kind of experiment actually highlight the possibility that sometimes in very particular cases, we can just rely on some very brief or short-term representation to handle some tasks which might look very complex. So that's fine.